The story begins in the early 1930s, when Washington state wanted a bridge that could connect Tacoma and the Kitsap Peninsula. At that time, the only way to cross the water was by using boats and ferries, which slowed down travel and business. People pushed for a suspension bridge, something tall and elegant that would stretch across the deep channel known as the Tacoma Narrows. Engineers, politicians, and local communities all believed this project would transform the region. But there was one major issue: the water below was fast, the winds were strong, and the channel was narrow. Engineers knew this crossing would be difficult. The challenge was not just building a bridge, but building one that could survive violent wind currents that constantly passed through the area. Even with the concerns, people wanted a modern design, something thin, lightweight, and beautiful. A young and ambitious engineer named Leon Moisseiff became one of the main designers. He was respected for creating elegant suspension bridges. His philosophy was that bridges should be flexible. According to him, bridges didn't need to be extremely heavy or stiff. They could be slender and still be safe. So he used that design approach for the Tacoma Narrows Bridge. The bridge was given a very thin roadway supported by only two giant cables, with minimal reinforcement steel underneath. Construction finished in July 1940, and the bridge immediately became a tourist attraction. People came from all over the region just to stand on it and admire how sleek it looked. The bridge even earned a nickname on the very first day. As traffic moved over the deck, the entire roadway began to rise and fall like a rolling wave. Cars driving on it felt the bridge gently twisting, bouncing, and swaying. Local newspapers quickly called it Galloping Gertie. The name stuck, and soon everyone used it. The swaying didn't stop. It became a daily routine. People were fascinated by it. Some even enjoyed the strange motion. Drivers would take the bridge just for the thrilling feeling of the deck lifting beneath their car tires. Teachers brought students to watch the movement as an educational experience. Even though some people felt uneasy, engineers told the public that the bridge was safe. They said the swaying was uncomfortable but not dangerous. As long as the bridge stayed within expected limits, everything was fine. But the truth was different. The bridge wasn't just flexible, it was too flexible. The slender design that saved money also made the structure extremely weak against strong winds. Engineers installed heavy cables and shock absorbers to reduce the movement, but nothing seemed to solve the problem. Every day, the bridge behaved in a way no major structure should. And yet, the city kept it open, unaware that a disaster was slowly building with every gust of wind. The first serious warnings came just a few months after the bridge opened. Engineers noticed that even moderate winds could cause large vertical oscillations, and under certain conditions, the bridge began twisting in a motion engineers had never fully anticipated. This twisting motion was unlike normal swaying. It was not just up and down, but rotational. The deck would tilt from one side to the other, sometimes violently, creating dramatic waves along the roadway. Witnesses said it looked as if the bridge were alive, moving on its own, almost as though it had a mind. Even birds struggled to fly near it, buffeted by unpredictable currents created by the structure's movement. Local newspapers reported on the strange motion almost daily. Some journalists described cars bouncing like corks as drivers crossed, and pedestrians had to cling to railings to avoid falling. Engineers tried several solutions. They added cables, stiffened the structure slightly, and monitored every movement. Nothing truly stopped the unusual oscillations. Still, public interest only grew. People began to see the bridge as a spectacle rather than a threat, and tourists flocked to the site to experience it firsthand. The problem lay in something called aeroelastic flutter, a phenomenon that engineers of that era did not fully understand. Simply put, wind hitting the bridge at certain speeds could create a self-reinforcing motion. Unlike normal vibrations that eventually die down, this type of motion grows stronger over time. The very flexibility that was intended to make the bridge elegant and efficient turned out to be a critical weakness. The bridge's thin deck acted almost like a ribbon in the wind. Small gusts created larger ripples, which in turn amplified the effect until the motion became extreme. On November 7, 1940, the winds picked up to about 40 miles per hour. It was not a storm by any usual measure, but the bridge had already been weakened by months of oscillation. People in nearby buildings watched as the deck twisted and writhed dramatically, moving in a rhythm that seemed impossible for a solid structure. Cars on the bridge were either trapped or forced to abandon their journey. Some drivers tried to cross but turned back, unable to keep control on the tilting surface. The bridge's motion had reached a point where it could no longer be considered safe. Engineers and officials tried to monitor and control the situation, but they were powerless. In less than an hour, the twisting motion intensified, and cracks began to appear along the supports. Suspension cables groaned under the unusual stress, metal girders bent, and the entire structure began to vibrate violently. It was a slow-motion disaster, visible to anyone who dared watch. For the people observing, it was surreal, both terrifying and mesmerizing, a spectacle that no one would forget. By late morning, the situation reached a catastrophic point. The twisting and undulating of the deck had created enormous stress on the suspension cables. Steel began to snap, joints failed, and sections of the roadway started to buckle. Onlookers along the shore watched in disbelief as the bridge moved violently, rising and falling in waves that seemed almost alive. Cars and trucks had been removed or turned back earlier, thankfully preventing major loss of life, but the bridge itself was beyond saving. Then, in a matter of minutes, the inevitable happened. With a tremendous groaning of metal and snapping of cables, the center span of the Tacoma Narrows Bridge collapsed. The massive section of roadway tore itself free from its supports, flipping and twisting as it plunged into the waters below. Huge waves splashed against the remains of the structure, carrying parts of the bridge downstream. Pieces of wood, steel, and concrete were tossed violently by the currents. The noise was deafening, a mixture of metal tearing, cables snapping, and water crashing. It was a scene no one could have imagined before seeing it with their own eyes. Remarkably, despite the dramatic collapse, only one life was lost. A dog named Tubby, belonging to a man filming the collapse, fell into the water when the bridge gave way. He survived by clinging to a floating piece of debris, and the footage captured of him struggling in the water would later become iconic, a tiny symbol of resilience amid a massive disaster. Beyond that, there were no other fatalities. Drivers and pedestrians had largely been warned or had chosen not to cross. Still, the economic and structural impact was enormous. The collapse caused millions of dollars in damage, destroyed the crossing, and left the region without its vital transportation link. The failure of the Tacoma Narrows Bridge became a pivotal moment in engineering history. Scientists, architects, and engineers studied the collapse intensely, trying to understand why such a seemingly modern and carefully designed structure had failed so dramatically. The disaster revealed the dangers of aeroelastic flutter and the importance of wind testing in bridge design. Future suspension bridges incorporated lessons learned from Tacoma. Bridges were made stiffer, stronger, and designed to withstand not only the weight of vehicles but also the unpredictable forces of wind and weather. In hindsight, the Tacoma Narrows Bridge serves as both a cautionary tale and a remarkable story of human ambition. It demonstrates the risks of pushing the limits of design without fully understanding the forces involved. At the same time, it captures the imagination, because the footage and reports show a bridge that almost seems alive, twisting and galloping before it finally gave way. It became an unforgettable example of how engineering, nature, and human curiosity can collide in dramatic and unforgettable ways. It acts with a flexible structure in such a way that the movement of the structure amplifies the force of the wind, creating a self-reinforcing cycle. Essentially, the bridge's slender deck acted like a ribbon in the wind. As the wind pushed it one way, the structure's flexibility caused it to twist in response, which in turn allowed the wind to push even harder. The motion grew stronger and stronger until the bridge could no longer hold itself together. What was intended as elegance and lightness in design had become its greatest weakness.